Hi, my name is Neelu Skipper, and I will be presenting effects of snow cover on luminescence dating of glacial moraines. Large glaciers and ice sheets in North America have melted as the climate warmed since the last ice age, which has exposed the boulders inside. Once exposed to light, the boulder surface begins to lose its luminescence signal, which is a measurable amount of blue light. That can be stimulated by shining infrared light onto mineral grains such as quartz or K-feldspar. With time, the signal empties to greater depths within the boulder. Using luminescence dating, we can find the date that the rock was exposed and therefore the date that the glacier melted at the location. To estimate how long the boulders have been exposed to sunlight, several important assumptions are involved, which previous research has overlooked. Varying degrees of snow cover could influence the apparent exposure age of samples. In this study, we developed MATLAB codes to simulate fluctuating levels of snow cover through time to determine the effects on bleaching depth. With these results, we can more accurately estimate when glaciers are treated from specific regions, and this helps us to better reconstruct past responses of glaciers to climate change. This helps us better predict future melting of land ice in response to changing climate currently. This is an image of a boulder falling out of a glacial moraine. This one, it's frozen inside, and then throughout time, it becomes exposed. Moraine boulders are just chunks of rocks that have become frozen inside of glaciers as the glaciers eroded underlying bedrock. The glacier melts, the boulders fall out, and then the longer the boulder is exposed to sunlight, the deeper into the boulder interior the luminescence will bleach. By estimating the date that multiple boulders at multiple locations were exposed to sunlight, we can find the timing and rate of glacial retreat. Studying how glaciers behaved in the past helps scientists more accurately predict how modern glaciers will respond to future climate change. OSL profiles inform sunlight exposure ages. So this is a rock which could be taken from a terminal moraine, which is the furthest extent that the glacier reached, and we can find how sun exposure affects the depth and the OSL intensity. Moraines form natural berms as they recede. So this is a terminal moraine, and then these are recessional moraines, which are the debris and piles of boulders that they leave behind. This is the furthest extent, and then these are just the indications of timing of glacial regression. So this raises some research questions. What if wintertime snow cover lasted longer in the past? Would this affect bleaching depth, and if so, how? What if extended winters occurred over thousands of years? In figures 4, 5, and 6, there are simulated OSL depth profiles for the same sample over 1 year, 10 years, and 100 years. In all three cases, the rock was exposed to sunlight for various amounts of time each year, which mimics seasonal snow cover. So this pink one, it was 1 month of the year sunny, and then this 12th one at the bottom here, it's 12 months out of the year sunny. So that would be like if there was no snow cover for the entire year. So in this one, you can see that the distribution of each simulated OSL profile's bleaching depth is summarized as x half, which is just the depths where the signal is halfway bleached. So this right here. This is fractional saturation, which is the amount of luminescent signal that the rock has accumulated. 0 means that the signal is completely empty or the sample is fully bleached, and 1 means that the signal is full. If rocks have been exposed to sunlight for more years, they have deeper bleaching depths, as well as rocks with more months of sun per year. So our big takeaways for this are that longer periods of snow cover each year contribute to a shallower bleaching depth. So the more sun, the deeper the bleaching depth is. As longer periods of snow cover repeat continuously, bleaching depth increases. So for example, this is just if there's a long winter for 1 year, this is for 10, this is for 100. So as you can see, all of these continue to go down. And we also know that for each simulation, the difference between the greatest and lowest hypothetical bleaching depths are equal. So for this pink line and for this dark purple line, for example, we would do like the months of year sunny 1 for 1 year and for 100 years. This distance is the same for months of the year sunny 2 months for 1 year and 100 years. All of these are the same distance. For future work, we will estimate the potential bias on exposure age calculations for if winters were significantly longer in the past. So there is a difference between if it was 1 month of the year sunny versus if there was no snow coverage at all. We will also see if there is a significant difference noted, then we will have to correct or mitigate this correct to determine more accurate time estimates for glacial retreat. Here are 2 moraines which were previously dated with cosmogenic beryllium-10. This is good because they have an independent age that we can compare to the age that we get using OSL. We will date these in the summer of 2024. For my references and acknowledgements, I just want to thank Carissa Cordero, Diana Valenzuela Davila, Ayush Joshi, and Jeffrey Warburg for their advice and all the help that went into making this. Thank you. Bye-bye.